All right. So were you able to finish them?
I was working on them. I just got stuck.
Mm-hmm. Let's see. Were you able to do the first one though?
Uh, I did the what's it called? I did the dot product for it, but I was confused on like why there was a y, but the other one didn't have like a variable attached to it.
Let's see. Right. So question asks us if two vectors here, vectors this equals this and this equals that are orthogonal. Yeah. Um, that could be a typo. I mean, the y is really irrelevant. What they're asking is for whether these two are orthogonal or not. Right. So we're looking for the dot product of this to be 0, right, for these two to be 0. Right, so we just have to take 4, -3, 6, and dot it with 3, 0, -2, and check to see if that equals 0 or not. All right, so 4 times 3 gives us 12, -3 times 0 gives 0, and then 6 times -2 gives us -12. All right, so this comes out to be 0.
Okay.
All right, so let's see. So yeah, these two are orthogonal. Now, the next one says which of the following vectors are orthogonal and parallel. Now, hold on. I think we did this, though. Seems like we did this. No, I don't think we did. No, we didn't do it. Right, we didn't do it yet. So, you want to check to see which ones are orthogonal and which ones are parallel. So that means that you have to use all the combinations of these vectors to see which dot products give 0 and which ones don't. And then for parallel, right, the vectors are only parallel when their dot product equals the product of their magnitudes. Right.
You said that's for parallel?
Yeah, so for orthogonal, A dot B equals 0. And then parallel means A dot B is equal to plus or minus the magnitude of A times the magnitude of B. Right, so this is how you would do it using the dot product. So that means that what we're doing is we need to take A dot B, A dot C, and then B dot C, right? We need to take these three dot products, right? And then we need to look at whether they fit this first definition here or this second one here.
Okay.
All right, so go ahead, take dot product for AB, AC, BC. Let's see what we get there.
For A, B, I got -9, 3, and -3.
Okay, so AB is gonna give us -18, -2, -2. All right, that gives us -22. Okay, for AC, That gives us 6. Well, no, not 6. Because C has a 0 I. Say what?
I thought you're supposed to. I thought you're supposed to, like for A B. I thought you're supposed to do like B minus A.
No, A dot B. A dot B. Dot products.
Okay. Oh, so for AC it would be 0.
For AC, so C's I component is 0, so 3 times 0 gives 0. Then we got minus 1 times 2 gives minus 2, right? And then 2 times 1 gives plus 2. Okay, so AC, A dot C gives 0, so A and C must be orthogonal to each other. All right, now we need B dot C.
For B dot C, it's also 0.
Okay, so let's see here. So B dot C, we get negative 12. 0 plus 4 and then minus 4. Okay, so this is also 0, right? Therefore, these two are orthogonal to each other, right? So now we just need to check to see if A dot B is parallel, if A and B are parallel, because this A dot B is non-zero, right? So we need to check to see if this equals, we need to take the magnitude of A and multiply by the magnitude of B, right? We want to see if this value is the same as if you multiply these two magnitudes.
So we only look for if they're perpendicular. No, not perpendicular. If they're parallel, if they don't end up being 0.
Yeah, if they don't end up being 0, that just means that they're not orthogonal to each other. Right? Orthogonal means the two vectors are perpendicular. They form a 90-degree angle.
Okay.
Right? So if it's not 0, then that means they don't make a 90-degree angle. So what we're trying to do is see if the two vectors are parallel to each other. Right. Trying to see if this is the case, or maybe if this is the case.
So would it be, based on the formula, would it be negative 22 equals root 11 times root 44?
Yeah, let's see, right? Because if we do magnitude of B or magnitude of A, right, that gives us the square root of 9 plus 1, which is square root of 11. And then if we do magnitude of B, right, that gives us 36 plus 4 plus 4, radical 44. Right, so if we multiply them, with these two magnitudes, let's see what we get. So we got radical 11 times radical 44, and we're trying to see if it's the same as 22. Now, radical 44 is 4 times radical 11. Or sorry, radical 4 times 11. Right, so this comes out to be 2 times radical 11 times radical 11. So I factored out the 4 from this square root, and that comes out as a 2 in the front. And the radical 11 and radical 11 multiply to give just 11. So this does give us 22. Right? But here we have a negative 22. So the negative sign just means that they're anti-parallel, which means they're going in the opposite directions. So it's still the same, right? Because you just have maybe A is going this way and B is going that way.
Okay.
All right, so let me see. Okay, so what have you guys been working on so far?
Well, class is over, so.
Okay, so you guys took your finals already?
All
right. So, let's see. In your class, what did you struggle with the most?
I would say like when we were really doing like triple integrals and the whole like partial derivative part. That was where I think I struggled the most.
Okay, let me see. And when is your next class?
The school year's over.
But you don't have another class coming up next semester?
No.
So you're done with all of you've graduated, or is it?
No. Oh, no. Next semester I'm taking intro to engineering.
Intro to engineering. And you said you're majoring in computer science, or?
No, computer engineering.
Computer engineering. Okay. Okay. So, let's see. So when we're dealing with functions of multiple variables, right? Like f of x, y, f of x, y, z, etc. Right? When it comes to taking their derivatives, we sort of it's very similar to just dealing with a function of a single variable. The only difference is when you're in you're in 3D space. Suppose we have a function of x and y. Right? You can move in either the x or the y direction. Whereas if you only have a function of x, right, you can only move in the x direction, right, just back and forth. So that's why when you take the derivative of a function of x, right, say for example, in the xy plane, right, so say we're in the xy plane, and let's say we have a function f of x, right, we can only move back and forth, right? So say we choose any point on the graph of f, we can only move back and forth. Right? And you can see that there's a defined slope here, right? So if you take the derivative with respect to x, right, the change in y over change in x, you'll get a positive slope because this graph is sloping upwards. Right? So the difference is in the xyz plane, right? So when you're in XYZ space, right, now your function is not a curve anymore. It's kind of like a surface. Right, so maybe let's say you have a surface like this, right?
Mm-hmm.
Right, and let me just make some traces of the surface. Right. So if I say I take the shadow of this surface in the XY plane, right? So you can see if I choose a point on that surface, then its shadow lies somewhere on the XY plane. So the difference here is that in the XY plane, like when I have a single variable function, I can only move back and forth, right? But when I have a function of two variables, right, this we'll call it f of xy, right? Now I can move back and forth like this, right, along the y-axis, or I can move side to side, right? So I can change my x and my y, which means that the slope that I get depends on which direction that I go in, right? So if I decide I want to take one step in the x direction, right, my slope is going to look like this. Right? Maybe it's going to look this way, right? Because it's kind of sloping downwards.
Mm-hmm.
Right? But if I choose to go in the y direction, then my slope is not too negative. It might even be 0 because it looks like, walking along the y direction doesn't yield any sort of like change in height, right? Any change in z. So your slope might even be 0. Point being is that your slope is different depending on which direction you go in. Right? If I go in the x, it's one slope, and then if I go in the y, it's another. So we'll say in this case the slope depends on which direction you travel. All right, so whether x or the y. Whereas in this case, your slope only depends on x.
So basically, in like three-dimensional, it depends on more than one. While
Yeah.
x is
Yeah, right? So when you're in 3D and you have a function of x and y, your slope depends on whether you go in the x direction or you go in the y direction. So this observation is why we need partial derivatives, right? Because when you're taking the derivative, you're calculating the slope. But then you have to ask the question, what direction are you calculating your slope in?
And then what about z?
So that's the thing, right? Because our function is only written as a function of as a function of x and y. So the function itself is z. Right? So this is z equals f of xy. Right? So it's like how you have y equals f of x over here. Over here we have z equals f of xy.
Wait, why would it be? Why is it that so you said f of xy is the slope for x and y?
No, f of xy is the function. Right? So f of xy is a function. The slope is the partial derivative. Right?
Okay,
So
it's partial derivative. Okay.
Yeah, so what I'm saying here is that slope in x direction is df dx, right?
Mm-hmm.
And then slope in y direction is df dy, right? So f of xy is the function itself. So this is a function of two variables, x and y. All right, so function of two variables, x and y.
But then how does it equal z?
Yeah, because based on the value of x and y that you have,
Mm-hmm.
right, this function's output is a z value, right? So if you're at x is equal to, say, x is 3 over here, and y is 4 over here, so you're at 3 comma 4, or, you know, whatever point this happens to be, maybe over here. This point would be 3 comma 4, right?
Mm-hmm.
Well, that 3 comma 4 corresponds to a point up here above the xy plane.
Oh, like when you were talking about like a shadow?
Yeah, it's exactly, right? So the shadow of the point on that surface is on the xy plane, right? So whatever point you choose in the xy plane, there's a corresponding z value.
Mm.
Okay, so does that make sense?
Mm-hmm.
All right, so yeah, these are partial derivatives. Derivatives. So this is partial derivative in x direction. And this is partial derivative in y direction. Okay, so let's take a look at how we calculate partial derivatives. Right? So calculating partial derivatives. Right. So let's see here. So the rule is that when you're taking the partial derivative of a function, right, you hold all other variables constant, right, and you take the derivative with respect to one of the variables.
Mm-hmm.
Right, so hold all other variables constant. And let me see. Hold all other variables constant. And what else? What else? You take the derivative with respect to one variable. Right? So what's this mean exactly? Well, it just means that you're only walking in one direction, right? So say for example, we're back to this point again. Right, so we're back to this point, and we want to know the slope either in the x or the y direction. Okay, So we can choose to walk in the y direction, or we can choose to walk in the x direction, right?
Yeah.
If we walk in the x direction, that means that the y doesn't change, right? So if the y doesn't change, then the derivative, right, goes to 0, right? I mean, well, not the derivative. The y's remain constant. So when you take the derivative, all y values go to 0, right?
Mm-hmm.
Because your y remains constant. But if you decide to walk in the y direction, well, then your y is changing and your x remains constant. I think I might have been, yeah, your x remains constant. So if your x remains constant, then that means when you take the partial derivative with respect to y, all the x's go to 0, right?
Yeah.
So as an example, right, so as an example, say you have f of xy is equal to 2y squared sine of x plus 4xy. Right? So it's 2y squared sine of x plus 4xy. And you want to take the partial derivative with respect to x, right? So say find df dx. So that means all of our y's remain constant, right? So df dx, right? Our y's remain constant, and our x's, we differentiate those. So in this case, we'd only have 2y squared times cosine of x, right? And then over here, we differentiate with respect to x, so the y remains constant, so 4 times y. So same rules apply, right? Same chain rules and quotient rules, all that stuff applies. The only thing that's different is you keep in mind what's your variable and what's your constant. So say we're finding df dy.
Mm-hmm.
Right, so with df dy, we hold our x's to be constant, and we differentiate with respect to y. So in our case, the sine is a constant, so this will be 4y sine of x plus 4x.
Wait, so why wouldn't the sine x drop out?
Because the sine of x is a constant. So we're treating the sine of x as if it's like a 4 or a 2 or something. Right, and it's multiplying the y as a coefficient.
Oh, yeah, because we're supposed to say like we're supposed to do it in terms of y. That's why
Right.
for xy, the y drop.
Right, exactly.
Okay.
So you take everything else to be a constant and you differentiate with respect to that single variable.
Okay.
Okay, so let's look at another example, and then you can try this one.
Actually, let me see if I can find. There was like a partial derivative example that I had in class. If I can find it. Oh, this one's in terms of t.
Yeah. So whether, I mean, the parameters you use, regardless of the parameters, it's still the same, right? Same rules.
Okay.
Right. Okay. Let me see. Okay, so yeah, let's take a look at this one. So we have f of xy is equal to x times e to the power of x squared y. And we want to determine, so find fx and fy. So fx and fy are just different notations for df dx and df dy. All right, so let's start with fx. And let's see. So yeah, try finding partial with respect to x and partial with respect to y.
So, would that be 2x times e to the x?
Okay, so you said 2x times e to the x. Not exactly. So make sure to remember that when you take derivative of e, right, so the formula is if we have e to a function u, and d dx of e to the u is equal to du dx times e to the u. So this is u prime e to the u.
Wait, so that means the derivative of u times e to the u?
Mm-hmm.
So 2x times e to the x squared?
2x times e to the x squared. Not exactly. So let me show you what I mean. Let's say, for example, f of x is equal to e to the sine of x. Right? Then f prime of x is equal to cosine of x times e to the sine of x, right?
Mm-hmm.
Okay, so now let's suppose, let's make this a little bit different. Let's suppose now it's x times e to the 2 sine of x. And I'm differentiating with respect to x, right? So the difference here is there's an x multiplying the e. The x itself is a function. So now you need to apply the product rule, right, to differentiate this. So you're applying the product rule while at the same time applying the chain rule. Right? So if you did f prime of x, it would come out to be derivative of x, which is 1, times the e, right, plus x times the derivative of the e. So the derivative of the e, I've written that formula here, right? It's u prime e to the u. So derivative of the e, first let's put the x back, right? And our u is the numerator, is the exponent, right? 2 sine of x. So this would be 2 times x times sine of x, or sorry, not sine, the derivative, so cosine, times e to the 2 sine of x. Right, so we're simultaneously applying the product rule and the chain rule. Right, so let's look back over here and see how we can apply that Same concept here, right? So we want to take fx, right? We want to find partial derivative with respect to x. Okay, so fx means that we're going to have to differentiate this whole thing with respect to x while holding y constant. So our y is constant here. All right, so we're going to apply the product rule. Right, so partial with respect to x here is going to be e to the x squared times y, right? Because derivative of x is just 1, plus x times the derivative of e to the x squared y. So let me write it again, same thing, but I'll just write it a little bit more clearly. So this is going to end up being dx dx or let me write it like this, dx dx times e to the x squared y plus x times d dx of e to the x squared y. Right, so it's just a product rule here. Right, so this part here just becomes e to the x squared y, whereas this part becomes x times the derivative, the partial derivative with respect to x of e to the x squared y. Now, the formula, remember, was u prime times e to the u. So our u prime is the derivative of the exponent, right? So that's 2xy, and times the e itself. Right, so if I simplify it out, this is 2x squared y times e to the x squared y. Okay, so you got to keep an eye out for the regular rules for derivatives, right? Product rules, quotient rules, chain rules, all of that.
I'm confused on that second part. The x, the x partial over x.
This one?
Yeah.
Yeah, because product rule, what does the product rule say?
Isn't it derivative first times the second?
Mm-hmm.
And then
So
the first times derivative first times the second. And then first times the derivative for the second
right,
one?
so yeah, f prime times g plus f times g prime. Right, so derivative of the first, right, so dx dx times the second, e to the x squared y, plus the first times derivative of the second.
Oh, the x squared 2, that's supposed to go on the top?
The x squared y is, yeah, it's the exponent. Right, e to the x squared y.
So we're taking the partial derivative of the second, which is the x squared.
Yeah, no, the second is e to the x squared y.
Wait, so the y is included as well?
Yeah, e to the power of x squared times y. Right. The x squared times y is in the exponent. Right, so we're differentiating that entire function. Right, e to the exponent x squared y. That's one whole function.
So we're doing the partial derivative of e x squared y?
Yeah, e to the power of x squared y.
So then how did you get 2xy?
Yeah, because the derivative of the exponent is 2x times y, right? According to the rule, the chain rule for
Oh
exponential.
yeah, that's what's confused. The y is confused. So it's basically like if you were to write it down, it would be 2x times that y on the side,
Right.
then times. But then why did we write the original again?
Yeah, remember, if you have e to the u, if you take the derivative of that, it's u prime e to the u.
Mm, okay. Oh, so then okay, so the 2xy is the u prime times e to the u.
Right.
Okay.
Right, so we're just following the same rules. It's just that y is a constant. Right, so we're treating the y as a constant while applying the product rule and the chain rule. Okay, so it's important to work a lot of these problems out. The more that you work them out, right, the more intuitive they become. And let's do partial derivative with respect to y before we move on to the next thing.
So that would just be x e to x squared.
Almost. Yeah, x. No, not x e to the x squared. So let's do fy over here. Right, so now you're taking the partial derivative with respect to y, which means that all of the x's are now constants, right? Think of it as like all the x's are 2's or something.
Mm-hmm. So wouldn't the first x drop?
Mm-hmm.
Wait, no. Wait, we would keep the x, right?
Yeah, we're gonna keep this one, but you're gonna
Mm-hmm.
need to take the derivative of this with respect to y.
Yeah.
Multiply.
Yeah. Yeah. I think the e is throwing me off. So basically, it would be like if it was written down like regular without no e, it would just be x squared y. So then we're just doing partial of y, which would be like dropping it out, so it'd just be e x squared.
No. We're still, remember the rule. E to the u prime equals u prime e to the u. You need to always multiply by the original.
Oh, wait. So that means the derivative of the top respect to y would be x squared,
Mm-hmm.
and
It's
then
just x squared.
times e to the x squared y.
Right.
Hmm.
Right. So your u happens to be x squared y. U prime is equal to just x squared.
Mm-hmm.
So that means the partial derivative is going to be x times x squared e to the x squared y. Right, so there isn't a product rule going on here because the x is a constant now.
Hmm.
So now you get x cubed e to the x squared y. Does that make sense?
Yeah.
Okay, good. So you need to practice.
Mm-hmm.
Right, you gotta work on a lot of problems in order to get to the point where you're very comfortable So this is what we'll do. And another thing is, you also need to be familiar with some differentiation rules, right? So like derivatives of e's, logarithms, that kind of stuff. Okay, so let's take a look here. Right, so remember the original rules apply for differentiation, product rule, quotient rule, that kind of stuff.
Mm-hmm.
The only difference is you're holding one of the variables constant. All right, we'll start out with a very easy one. Just like this. All right, so the goal here is to find both partial derivatives. Right, so this one, so you're looking for fx and fy. Right, now you're gonna need this, let's see, you're gonna need a calculus, derivatives and limits. Okay, I don't think you have this yet, but I'm going to, this is a formula sheet for different basic calculus rules, right? But these all apply for partial derivatives, right?
Mm-hmm.
So whether the variable is x or y, it's the same rules, right? So the main ones that you want to focus on are the common derivatives here, right? So so the common derivatives in this column here, these are very important to know. And then, of course, the chain rule, right? So the E, the rule for E that we were using is right here. Right, so if you have e to the power of f of x, you take the derivative, it's f prime times e to the power of f of x. Right, so this one is very important, as well as this one for the natural logarithm. Right, so these two over here, I mean, honestly, let me see. This one, this one, this one, this one, and this one, and this one.
All right, what's the first one?
Yeah, the first one is a power rule for functions. Right, so we have the regular power rule over here, right?
Mm-hmm.
d dx of x to the power of n. But we have a similar rule for functions. It's just that you're applying the chain rule. Right, so n times the same function to the power n minus 1 multiplied by the derivative of that function. Right, so I mean, a quick example of that is, say you have x to the power of 4 plus 6 sine of x, and you're raising that to the power of 10. Right, so if you differentiate that, you're gonna get, you bring the n down, right? So 10 x power of 4 plus 6 sine of x, power of 9, then you multiply by the derivative of the inside. So x cubed plus 6 cosine of x. So these are chain rule formulas, right? And those same formulas apply to partial derivatives as well.
Okay.
Okay, so I'll put this one in the what's it called, in the Google Drive, right?
Mhm.
And you can use that to sort of help guide you when you're doing derivatives. So yeah, let's take a look at these problems, and then after that we're gonna try to get to the next topic here, because the goal of knowing and understanding partial derivatives is to help you when it comes to finding the slopes of surfaces, and also when you start doing directional derivatives, right? So let's start with one.
For the first one, for f of x, would it be 2 minus 5y plus 3?
2 minus 5y plus 3, okay. So we're taking the derivative with respect to x, right?
Yeah.
Right, so that means that all the y's are constants, right? So, yeah, so we're treating this 5y as a constant.
So that means the 3 would still be, no, the 3 would be gone.
Right, the 3 is going to be gone.
So it'd be 2 minus 5y.
No, just 2. Right, because the 5y is a constant. Right? So that means that derivative of a constant is equal to 0. Right, so this is a constant, it goes to 0.
So that means for f of y would just be negative 5.
Right. Right, so fy gives negative 5. Okay, so let's look at problem 2. So problem 2, we got x times square root of y. Right, so x times square root of y. So we're looking for partial derivative with respect to x, and then with respect to y.
Would it just be square root of y?
Okay, so with respect to x, yeah, this would just be square root of y. And then partial derivative with respect to y.
Would it just be x?
No, not x.
Is this where we would have to use product rule?
No, because the x is a constant. Right, so try rewriting this with the y as a power, right? So x times y to the power of a half. Right, so you're holding the x as a constant.
But wouldn't it be, if you're doing the derivative, wouldn't it be x 1/2 y?
Yeah, right. So we bring the 1/2 down times x, then y to the negative 1/2. Okay, what about number 3?
So that would that be for f of x? Would that be y times e to the xy?
Okay, so right, y times e to the xy. And what about for fy?
So that'd just be x times e to the xy.
Right, so x times e to the xy. Okay, good. Now, let's look at how we can use, let's see. Yeah, we can use partial derivatives to evaluate slopes. So one thing we want to keep in mind, well, let's write down a few things here. There's some stuff about notation. Okay, so I already talked about how df dx of xy is the same thing as fxy, right? Fx of xy. Right, so this is the same thing as writing z sub x, because your f represents z. And this is the same thing as the partial derivative of z with respect to x. Okay, and let me see. Now, this is how you calculate the partial derivatives, right? But you can also evaluate the partial derivatives at certain points. Okay, so say the first partial derivatives of a point at a comma b are denoted by dz dx dz dx at ab equals fx at AB, right? And dz dy at AB equals fy at AB.
Wait, so it's like taking the partial derivative of a point?
Yeah, so it just means that you take the partial derivative and then you evaluate it at a point. So after you find your partial derivatives, you plug in a point, and that tells you the slope at that point. All right, so let's see how we can evaluate the partial derivative. at a certain point. Evaluating partial derivatives. Okay, so you always have to take the partial derivative first and then substitute in the points.
Hmm.
Okay, so let's say for f of xy, for f of xy equals x times e to the x squared y. Find fx and fy and evaluate. Right, so we're evaluating each at the point 1 comma natural log of 2. All right, so we're going to evaluate it at the point x equals 1, y equals natural log of 2.
Wait, so does that mean? I'm kind of confused. Does that mean like for any place we see x, we plug in 1?
Yeah. Right, so that
Well,
means we need to first
Yes, it-
calculate
yeah.
we need to first calculate the partial derivatives. Then we substitute the points.
Mm.
All right, let's find fx.
Mm-hmm.
Right, so our fx is going to be, it's a product rule here, right? So it's going to be e to the x squared y plus 2x cubed e to the x squared y. So this is our partial derivative with respect to x. Now let's find fx at 1 comma natural log of 2. So everywhere we see x, we substitute 1. And everywhere we see y, we substitute natural log of 2. So it looks like our first term here is just e to the natural log of 2. For our second term, this becomes 2 times e to the natural log of 2. Right, so the result is we have 3 times e to the natural log of 2.
Mm-hmm.
And since the exponential and the natural log are inverse functions, we just have 3 times 2. Right, the e and the ln cancel to give 2, and this gives us 6.
Okay.
All right, so this means our slope in the x direction when we're at the point 1 comma natural log 2 is equal to positive 6. All right, so we do the same thing for fy, right? So fy, this just gives us x cubed e to the power of x squared y. And now we can take fy at 1 natural log 2. So we substitute all x's with 1s, the y's with natural log 2, and we get e to the natural log 2.
Mm-hmm.
And again, we just get 2. Right, so we have different slopes depending on which direction we go in. If we go in the x direction, we get a slope of 6. And if we go in the y direction, we have a slope of 2.
Okay.
Right, so this x e to the x squared y is just a surface, right, in xyz space. So when you're at a certain point on that surface, right, you're going to have different slopes depending on whether you're going in the x or y direction. So let's take a look at another surface that we can take the partial derivatives of. So this one, we have to find the slopes in the x direction and y direction, right, of the surface. Right, our surface is f of xy is equal to negative x squared over 2 minus y squared plus 25 over 8. Right, so this is our surface, and we need to take the partial derivatives of this, right? And we want to find the values of the slopes at the point 1/2, 1, and 2. Right, so this is our x coordinate, this is our y coordinate, and this is our z coordinate. Okay, so same process. Same process. First, we want fx, right? So partial with respect to x. So with respect to x, we just get negative x, and that's it. And then partial with respect to y, well, this is just negative 2y. Right, so now we want to evaluate fx when x is 1/2 and y is 1. Right, so when x is 1/2, we just get negative 1/2. Right, now we do the same thing with fy when x is 1/2 and y is 1. Right, so now we only have y's involved, so we just substitute our y directly, and we get negative 2. Right, so first thing, you're calculating your partial derivatives first, then you're substituting in the points they gave you. Okay, does that make sense?
Yeah.
Alright, cool. So we'll stop here for now. But let's see. Chain rules of functions. Right. What we can do next time is we can look at how to apply the chain rule to functions of multiple variables. How do we do that? And what we might do after that is look at vector valued functions.
Okay.
Yeah, how to evaluate vector valued functions. Then we'll come back and do directional derivatives. And
Wait, is that before or after like we do multiple like partial derivatives, like how we had like 2 or like 3?
yeah, that's what the chain rule part is going to be about.
Okay.
Because that's going to be for when we have, x and y, but both of those are also functions of other variables.
Okay.
Right. So once we've done that, now after that we can look into directional derivatives, gradient vectors, and let me see. Yeah, I think that will be good. And then from there we can move on to the other stuff, because after that we need to look at tangent planes and normal planes and stuff. Similar to what we did I think last week. We did that.
Okay.
All right, cool. So I'll save this up. I'll put it up on the Google Drive, and I'll see you next week.
Okay.
All right, man. Have a good one.
You too.
All right.